As Tom Berkeley sort of said before the break, Jim got interested in e-science. And so much of the rest of what we'll hear from today is his contribution to e-science. And so he started off hooking up with a bunch of astronomers and working on the Sloan's sky survey. And we're delighted to have here today Alex Szalay. And I apologize for butchering your name. To tell us about his work on the Sloan Sky Survey. So, Alex?
Thank you very much. So I would like to tell this story about Jim becoming an astronomer and how this happened. And so for the background, so we started this amazing project, the Sloan Digital Sky Survey, around '92. And the goal was to create something like the Human Genome Project for astronomy, so to map out the whole sky. And it was certainly going to generate a lot of data, especially it seemed to be a hell lot of data in 1992 when we started. So it takes both images of the sky and it also creates a three-dimensional map of the universe. And I'm also glad to say that after having worked on this from '92, 2 weeks ago we finished. So 2 weeks ago the survey is officially over, and the last data. So this story really began in '92, but when I'm a cosmologist by training, and I knew nothing about databases, but that was one job that nobody wanted to do. So this is how Hopkins ended up doing the archive for the Sky Survey, and I was working on the statistical distribution of galaxies, and I figured that since I can't do the statistic if the data is not properly organized, so we may as well do the archive and make sure. And so we started along. So the Sloan project, SDSS, needed a database. And we were building the archive. We were, an object-oriented database looked very cool, so we started out with that, and lots and lots of C++ code. And then we had an SDSS meeting in Seattle because UW was one of the partners. And then I had dinner with Charles Simonyi, and Charles mentioned the TerraServer work and Jim, and then called Jim right after the dinner. And a few weeks later, I flew to San Francisco to talk to Jim. And, this was one of those days that nothing was the same afterwards. So we started to talk more and more. And Jim came to Baltimore, and we started, to talk about what could we do, what are the similarities between looking at the sky and looking at the Earth. And we realized there are lots of similarities, so everything is geospatial, everything is like a sphere, and so on. And then Tom Berkeley and Don Slutz were already working a lot on the TerraServer at the time. So Jim came along to Baltimore and came into our computer room, sort of stuck his nose in, and he said, well, you got the database layout all wrong. And we sat there stunned, all these astronomers. And so Jim was smirking, and then a little bit later explained, so he actually did not look, he listened. And he heard the disks rattling, so that meant we didn't have enough sequential I/O. It was too much random access. But he certainly sounded like, the car mechanic who comes in with a hammer and just hits in the right spot and the car starts working. And so that was our introduction to Jim. And so basically, we were playing around with ideas for quite a few years. And the project was in a development stage, so there was still no data. And everything was a little bit slipping. But what we wanted to have is an easy visual access to new data, and to make it sure that people can get to the data as it is hot off the press. And also, Jim was very keen on showing that we don't have to do a cumbersome interface, even if the data is a lot. So we expected to have terabytes of data. And also, he was very keen on digital libraries, digital publishing. So this was a perfect test bed on how to publish this new kind of scientific data. Anyway, and so we basically, there was an Intel meeting around January 2000 in San Francisco. And Intel gave us some computers for this. At that time, it looked like, to store a terabyte of data, we needed probably 20 of those machines. And so we came along, and Intel wanted a show and tell. So I flew out to San Francisco, and we took a computer from Jim's lab over to this conference. And my son Tomas came along, who was 13 at the time, and he was the person manning the booth. And we did a little interface, basically just showing off what it would look like using some of the test data from Sloan. And in the meantime, so people came along, they were very interested, and then Tamás told us after that, no self-respecting school kid would actually use an interface like this. So this told us that we needed, first of all, that we had a target audience. And so we decided, so Jim had one of his big laughs at the time. Tamás probably doesn't even remember this, but I do, because that was when we decided that we are actually going to build a Sky server, and it will be for high school kids. So that will be our focus audience. And so then suddenly data started coming, but it only came, so we had a hard deadline. That was June 6, 2001. That was the annual meeting of the American Astronomical Society, where we promised that we would show an early data release. Basically, so the data, it was not that much. It was about 100 gigs at the time. The trouble was that the 100 gigabyte only started arriving about 2 weeks before the meeting. So Jim and I, being cowboys, we basically then put in about 2 weeks of 20-hour days, and we got it working. But we were literally dropping at the end. So the images were converted in Photoshop scripts, so we were hacking it left and right, and basically we got some hardware. So it was really done by a very small number of people and all volunteers and so on, but we actually got it working. And it was presented as a public outreach tool for the Sloan Sky Survey at the time. So the first official big release of the data, which was about a terabyte, came about a year and a half later. And by then, we really kind of put together a proper framework. So Anitakar took over, so we wrote a proper loading pipeline and so on. And then the whole interface got a proper facelift. So Curtis and Asta Roseway chipped in, and they really made the site look very nice. And then we started to build simple services, simple visual tools. We published the APIs, and then Jim created, he said we have to create a personal version of the Sky server. We did not do an enterprise, so this was the enterprise version. We created a personal version, and we wanted to create also a professional version, being Microsoft. But we stopped actually at the personal level. It fit on a CD-ROM, and you could download at that time as copy of SQL Server for personal use. And we basically gave a 6 square degree piece of the sky which had the same database structure, so people could actually play with this on their laptops. And the content was rewritten. We created educational exercises and so on. And so this was really the big transformation of the Sloan, and it went on, year by year. We had a major data release, and the last one is going to come out at the end of this year. And so we built a whole bunch of visual tools. We have our 3 trillion pixels of images, and we built a really nice interface, emulating in many ways the Terra server interface. And these images are still the same, essentially the same processing of images still survives, and they are now, the same images are both in World Wide Telescope and Google Sky, by the way. And we realized that geospatial searches will be really essential for astronomy, and the Sloan has a really complex boundary. So we have of the order of 60,000 different regions that describe different geometries of the survey. So we first built a GIS-like library in C++, but then over the years, we decided that we wanted to have a much more complex region algebra, and we coded about 7,000 lines in SQL. So only Jim can do this. So write computational geometry and SQL and look it elegant. So it was just amazing to watch him, as this code was created, and it actually worked. And so by now we've converted it all to C# and so on, but it was, I learned so much about SQL programming watching him do the magic. So, and The last paper we wrote with Jim around Christmas '06 was analyzing the user logs. So we logged everything from day one because we felt it's very important. This is the transition of the age when people are using e-science. We are transiting to this new way of doing science. So we logged every user hit. And essentially, we were stunned at the results. So there are 430 million web hits on the site in 6 years. And we had about almost 1 million distinct IP addresses. What is amazing about this is that there are only about 10 to 15,000 professional astronomers in the world. So most of the usage came from outside the astronomy community, from interested amateurs and so on. At the same time, we delivered about 100 billion rows of data over the web. And what we found in the usage statistics, that everything was a 1/f power law. So there was no distinction, no distinct breakpoint between where the professional astronomers kicked in and the public started. It was all a continuum. And then this was only last summer, but we did a mashup. We took the Sloan images of the brightest galaxies and we put it up on the web and asked people to visually come in and classify it. And this was, again, amazing. In the first day, we got like 15 million hits. And a school teacher in Holland around Christmas '07 made a truly interesting discovery. She discovered this blue object next to a bright galaxy, and it turned out to be a totally unique object in the universe. We just were notified 2 days ago that we got Hubble Space Telescope time to observe this object that was discovered by a school teacher. So, and this is... So once the Sloan project started to evolve, it was obvious that this is by no means a singular project. So even within astronomy, people were doing very similar things on other telescopes and in other wavelengths, and also above the atmosphere and from the ground and in radio. And much of this data was already online, so the astronomers have been pretty good about this. So it was clear that the internet has the potential to become the world's best telescope, but the problem is that everybody had a different interface. And so the goal was then we started a project called the Virtual Observatory, which took off like wildfire, both within the US, that led to the National Virtual Observatory. And we have now 18 countries in the world which have their own virtual observatory, and this form a loose organization. And Jim was really very good. He came to all the early meetings and basically encouraged astronomers to do this and kind of guided us every step along the way. And SkyQuery was one of the early applications of .NET. And so when .NET came out, there was a programming contest for students, and some of the grad students from Hopkins wrote an application where basically they could take different catalogs at different parts of the world and do a remote join between them. So this is something like, asking a question that I would like to find out that of all the books of Asimov which have a blue cover, give me the ones where Barnes & Noble is $2 cheaper than Amazon. Basically, that was the task, and we had no idea what .NET is, and in 6 weeks, the student essentially created an application. It won the second prize. And so then we set up an application. And Jim liked to say that you have nothing to fear but success or failure. And so the end of this project was that it was so successful, many people wanted to use this in the astronomy community. So this is one of the common patterns. But they didn't want to stop at a small patch of the sky. And they wanted really to do 1 billion objects, cross billion objects. And so Maria Nieto Santisteban has been working on her thesis to essentially create a much faster algorithm. So now we can do it in about 1 hour to cross-match 1 billion objects against 1 billion. And we are now building a parallel engine that we can do this in 3 minutes. So, and this all grew out. So Jim came up with a new spatial join algorithm that actually scaled to this and was easily parallelizable. So this is a slide from Jim. He gave a physics colloquium at Hopkins, and he stunned the audience when he said he loves astronomy. I love you guys because your data is worthless. And he really meant it in the most complimentary sense, that it has no commercial value. He doesn't have to go to the Microsoft lawyers to get non-disclosure agreements and so on. And you can give away the data, and we can share the data everywhere. And it's great for experimenting with search algorithms, because it's also real, well-documented, has high-dimensional features, spatial-temporal features. It's diverse and distributed. So it has all the things of the real data, and it is big. So Jim had this amazing ability to go native. So once, when he was on sabbatical during one of these years during the Sloan, so he took a few months off and went on his sailboat, and he took a bunch of astronomy books with him and came back an astronomer. So it was really amazing to watch how he picked up the jargon, understood the principle in no time. And you know, he participated actually on astronomy research papers as an equal partner. So this shows him when the Sloan telescope was dedicated in June 2001. And Gordon showed already a version of this slide. So then we started at this point realize that this is much bigger than just astronomy. It started popping up in every area of science, you know, from biology to oceanography. And so Jim had a wonderful set of principles for data engineering, how to approach, which worked. He approached me with the 20 queries the first day I met him. But so let's go through this. So first of all, so he made the point that scientific computing is, these days, it's much more about data than CPU. It's really our ability of, there are bigger and bigger data sets generated, and even the computers are generating these huge simulations, which we are reaching the point when we cannot do anything with it. So we need a new solution for analyzing large scientific data, and the traditional ways that people downloaded all the data to their computers and analyzed it will not work. First of all, because they cannot download it, and even if they could, they couldn't store it, and if they could store it, they still couldn't process it. So we have to take the analysis to where the data is. And he had this principle of 20 queries, that give me your 20 queries and I design your database. And so this means and he didn't even mean SQL queries. He meant English ways of describing what you wanted to do with the data. And it was an amazing way to short-circuit the communication between somebody from astronomy and a database engineer. And I have seen this working, you know, in many different contexts. So we went around to NCBI to talk to the molecular biology people. So basically, in every context, Jim first said, give me your 20 queries. And once the people gave those, they were forced to think very hard about why did they really want the data to begin with. And it is something, you know, this is an amazingly effective way of approaching. And his other approach was going from working to working. So he said, let's not do a huge engineering thing. We are cowboys, let's do this. And let's build something, and then we modify it as we learn along the way. And it turned out, again, in this way, when, you know, one day there were no .NET services or web services, then next day there are web services, you know, so the outside world is changing so fast. If we design a big grand system, we will never catch up. But Jim's approach works. And so we have applied now this to many different areas, and Jim was, you know, the moving force behind all this. And so there is another story. So my wife is an environmental scientist. She's interested in soil monitoring, soil processes, and the soil ecosystem. And once we visited Jim and Donna in Berkeley, and Jim took us over to Berkeley, to the Intel Berkeley lab, to Wong, who was at the David Culler's lab at Intel at the time. And Kati gave a talk about what she would like to do, how she would like to use the motes in the soil, and we got a shoebox of motes. And then we started to build a little network out of this. And today we are just about deploying a huge network with thousands of sensors and hundreds of motes, with generating hundreds of millions of measurements. And then Jim said, okay, but you see, this is not about data collection, it's about what you do with the data. And so he said, let's take the SkyServer and let's see what we can do with it. So we took the SkyServer database, and in about 2 weeks, we were able to rewrite it to handle all the sensor data. And then Jim said, okay, but this is not good enough. Scientists really want to see these aggregates, so let's build a data cube out of it. And along came Stuart, and Jim and Stuart built a data cube. To my knowledge, this is the first application of data cubes in science. And so we built a data cube out of this sensor data. And basically, we have this now up online on the web. That's lifeunderyourfeet.org. And again, we started with the 20 queries. So it's the same pattern, and it worked. So this is when Jim was visiting the sensor lab. So Jim drew this diagram, and he asked, okay, so Alex, where are we on this diagram? So this is your life. So this is work, and then you start going to, as a graduate student, you start to work. Then you start to go to meetings, you start to go to travel. And as you get older, you don't even travel that much, and you don't even go to meetings that much. People come to you, and you take them to dinner. And I was struck by this. But Jim tried to make this go out of the box. So he turned the two-dimensional into a three-dimensional diagram, and he never, ever quit working. So he was always cranking out code. So it was really amazing to watch him. So if he couldn't write a few hundred lines of code in a day, it was a bad day. And he loved tinkering. He loved tinkering with code. And we very often started the day as Jim was walking to the office from home. Then he called me on the cell phone, so that's how we started the day. Then we had a bunch of other phone calls during the day. And then before I went to bed, I talked to him one more time. And it was just an amazing ride all those years. So, this was one of the trips that we took out to Bark and saw Jim. And on a very personal note, when you get older, it's very rare that you make friendships that really change your life. And I think meeting Jim was one of those events. So certainly my life took also a very different turn after we started working together. And I would also pay a tribute to Jim, a person who changed astronomy. Thank you very much.
So following up Alex's talk, we have another astronomy talk on building the Worldwide Telescope with Curtis Wong.
Okay. I actually have only gotten to know Jim fairly recently. Actually, in about 2000, Gordon Bell used to make this habit of coming to my office and plopping down on my sofa and just asking me what's going on, and we'd talk about things. And one trip in 2001, he brought along Jim Gray. And if you're looking at this program here, it's this center picture, him sitting on my sofa. But he would, we sat down the first time, and he was asking me all these questions about the things that I was doing, and I didn't know anything about databases. My field is really more interaction, media, and design. But he listened through a lot of that and didn't say too much, but he asked a lot of questions about some of my work, and he asked if he could have some examples of it to take back and play with. And I thought, well, that's really interesting. And then he gave a talk at Microsoft Research a few months later where he gave this talk called Where Databases Meet Astronomy. And at the end of the talk, he said, if you're a visit person, we need you, and we know it. And what he didn't know, because he didn't talk too much about his project in that first meeting, was that I had been interested in doing an astronomy project for many, many years. I did a project at a little company called Continuum that was owned by Bill Beck in '93, and that project didn't quite go because the technology wasn't ready yet. And in listening to Jim's talk about taking astronomy data and making it public, I thought, oh my God, this is the beginning of the opportunity when the data is going to be up there, and that we can create something that not just great for astronomy, but we can do some pretty wonderful things for education as well. And so I put together a PowerPoint to him called SkyServer, the virtual telescope, the world's largest telescope. And he was really excited about that idea of in that proposal, which is thinking about stories within the context of the sky and bringing those objects and connecting them to other information sources on the web. And at that time, I was really busy working on a number of projects related to Microsoft projects. And it wasn't until like about 2003, as Alex just said, Jim called me up and said, we just finished the second data release, and we really like you to help us design the website. I go, okay, be glad to do it. It was only like a day or so of work, but it allowed me to kind of get involved in the project. And what was interesting is that was just a little thing that was kind of a throwaway. But every time Jim would talk about SkyServer, he would say, and Curtis Wong, and then his name. I thought, oh my God. I said, Jim, I just did the little tiny thing. He said, it was really important. And Jim always put everybody ahead of himself, and his generosity really amazed me. And so it also made me feel guilty. I said, I really got to get working on this other astronomy project. And so I was still working on other research too, and by 2005, I got a call from Jim and actually an email from Alex. He said, Curtis, there's going to be this workshop of astrophysicists that are going to talk about data visualization, and we suggested that you give the opening talk. I thought, oh my God. This is really scary because I'm not an astrophysicist or an astronomer. But he said, go ahead, just do it, it's going to be fine. And I still have the emails for that. And so I gave my talk, and I thought they were going to throw me out. But I did talk about this idea of an educational product with stories, and it was really actually wonderful. A lot of them really loved the idea and said, if you're going to do this, we want to help, which was incredibly reassuring. And afterwards, Jim sent me an email, and I have this here. It says, attaboy, my sources tell me your presentation and presence at the workshop was a spectacular success, in all caps. He says, thanks and congratulations, and hope you had fun. So we were off and running, and I had a number of astronomers from that workshop and other places. The thing about Jim is you send him a little an update, and he'll send you back 5 other people you need to talk to. And so over the course of next year, I started meeting more and more people, and by 2006, we hired a new developer, Jonathan, who was also passionate about astronomy. And so at the beginning of 2006, we really started focusing on, okay, we're going to start to build this project, which we'd called the Universe Project. And by the end of 2006, we had a very rough prototype of the engine running, and we were showing it to Jim, and Jim was calling everybody, emailing other folks in Microsoft saying, you should see this, it's going to knock your socks off, another all-caps email. And we had hired an intern from Harvard Center for Astrophysics to work with us. And I was giving him this big detailed update on where we were and that we were really excited about moving forward. And that was January 18th, 2007. And a week later, we heard about that. And by the time of March came around, we were really, concerned and worried. But we were also thinking, this project wouldn't have happened without Jim. So we decided to name the project the Worldwide Telescope because it's a much better name, both in tribute to Jim and also for the purpose of what we were trying to do. And Rick did a keynote at TechFest that year and invited us to give a presentation of the engine, and that was sort of the first time we had done that. And so from TechFest in 2007 up until 2 weeks ago, Jonathan and I, and more recently an intern, have been working a lot of hours to build the Worldwide Telescope. And it was fortunately, when you tell somebody that you're working on a project that was inspired by Jim, and there are so many other people that came to join the project as a labor of love. And what I'd like to do is show you a little bit of Worldwide Telescope, and you'll be able to see this here. Let me. Can you turn the house lights down? Thank you. And this light too. Okay, so what you're looking at is the sky, of course, and hopefully the lights go down. So right here is the Milky Way in the summertime. And what we wanted to do was bring together lots of different surveys all in context. So what we're looking at here is the Milky Way through the visible light, through the Digital Palomar Sky Survey. But we also wanted to bring together lots of different data sets, including the WMAP, which is the microwave survey, which is cross-registered to the optical, or the dust map, or hydrogen alpha, or X-ray. We have, here's X-ray actually. We have 50 surveys right now that are cross-registered between each other. You can seamlessly zoom in to any artifact. This happens to be a supernova remnant from about 5,000 years ago. You can crossfade between any two surveys. This one happens to be visible light and X-ray. You can find other objects in the sky, high-energy objects. Here's another bright spot. Take a look at that. And you can see that is actually the Crab Nebula. But in the context, there are many other images of the crab as well. You can see this in the Hubble. So let's zoom right into the center of the Crab Nebula in the Hubble. But one of the really exciting things about Worldwide Telescope is the idea of creating an environment so that kids can create tours, actually astronomers as well. I think one of the things that a lot of people would like under a night sky is to have a very powerful telescope and somebody that really understands the sky to be able to tell you about what you're seeing. And so we have a number of different guided tours that have been created by, here's one by Alyssa Goodman, who's an astronomer at Harvard Center for Astrophysics. Thank you.
If we look at it in optical light, we see billions of stars shining together in a spiral pattern. If we look at the heat from M81 rather than the light, it looks like the false color orangey image we see here. This Spitzer Space Telescope image uses long wavelength cameras that can see heat, just like the one that took the picture of this cat. Galaxies are filled with tiny particles called dust that absorb the...
Even though it looks like video, what we really wanted was these paths in the virtual environment. So essentially, what you're looking at is totally interactive. So if I wanted to find out more information about this galaxy, you could just go and look up various information sources on the web, such as on Wikipedia or ADS, which is the Astronomical Data Smithsonian Astrophysical Database, and pull up relevant queries about papers that relate to that particular galaxy, such as from May, or encyclopedia entries, or other kinds of searches. As well as other source imagery and other things. If you wanted to see this object in other wavelengths, you could see what it looked like from the Spitzer, other wavelengths of the Spitzer. Or if there were other tours that related to this particular object, you could click and see those tours as well. We wanted the tours to be so simple that even kids could create their own tours. Here's an example of a tour that's produced by Benjamin, who's 6 years old, and I'll show you a little bit about this one.
Hi, my name is Benjamin. I am 6 years old and I live here. Actually, I live over here in a big city called Toronto. On clear nights when I look up in the sky, I see something like this. The tour I want to take you on is of the Ring Nebula, which Wikipedia, the Free Encyclopedia, also calls M57. I don't know what that means really, but I think it's like a jewel in the sky. The Ring Nebula is in the constellation of Lyra. Lyra is also where the brightest star in the sky is. This star is called Vega. The Ring Nebula is a little ways away from Vega over here. My dad says that he doesn't think the Ring Nebula is too far away. I read that it's 2,300 light years away, which seems like a very long bike ride. This is not how I see the Ring Nebula. I see it like this. The Ring Nebula was discovered a long time ago by someone in France. This picture of the nebula is beautiful. It looks like a precious blue gem in the middle of some red orangey stuff that looks like fire. I read that's because different gases give off different colors. You can see green, yellow, red, and blue. A nebula is what happens when a star like our sun dies. It lets out its remaining energy and expands, making lots of pretty pieces that one day can become planets. I think it's neat that stars can be so amazing for so long. I wonder what Vega will look like when it dies. That's my tour. I hope you liked it as much as I liked making it.
Benjamin consistently gets 5 stars from a lot of people. So there are a number of, sorry, Benjamin. There are a number of other things we can do in Worldwide Telescope too. We can access to planets, such as Mars. All of these can be included in the guided tours. We have the ability to include panoramas. So this is a Opportunity, the Mars rover Opportunity at Erebus Crater, or some other ones. Here's one, Spirit. And you can go and look at details of Martian rocks. But these are just demonstrations, and we're hoping to get more astronomers and educators creating other tours specific to this from JPL as well. Other things that Worldwide Telescope will do will also hook up to a real robotically controlled GO2 telescope. So if you have a MEAD or Celestron telescope, you can drive your telescope in the sky here, and the other telescope that you have will slew exactly to the same place as well. I'll just show you one more image, which is a nice image of M42, which is the Great Nebula in Orion. And I should do this. This is Frank Summers.
Welcome. I'm Dr. Frank Summers of the Space Telescope Science Institute. Let me show you one of my favorite places in Hubble's universe. We begin at the constellation of Orion. In mythology, Orion is the hunter. This 1690 drawing by Johannes Hevelius depicts him fighting Taurus, the bull. The stars of Orion are bright and easily recognizable by their X-shaped pattern. The 3 stars in the center represent Orion's belt. Hanging down from the belt is his sword. Within the sword are several clouds of glowing gas, called nebulae. The largest is poetically referred to as the Great Nebula in Orion. The Orion Nebula is a bowl-shaped structure carved by winds and radiation from hot stars. This image from the Hubble Space Telescope captures the nebula in amazing detail. The group of hot young stars near the top provide the stellar winds and the high-energy radiation that carve the bowl shape of the nebula. An earlier Hubble image showed the details of the region near these hot young stars. The 4 bright stars are called the trapezium. These stars are massive, hot, and young, only a few million years old. In contrast, our sun is about 5 billion years old. The energetic ultraviolet light from these stars heats the surrounding gas and makes it glow. The stars also emit strong stellar winds that help push away the gas. Evidence of these stellar winds can be found well away from the trapezium. This star, named LL Orionis, shows a long curved bow shock where stellar winds and radiation are blowing back the gas around it. Back in the trapezium, we find some strange tadpole-shaped objects. Their tails point directly away from the largest star, Theta 1 Orionis C. There are many of these objects, called proplids, which is a contraction of protoplanetary disks. Within each proplid, gas is collapsing to form a star. The gas feeds onto the star from a disk, and within that disk, planets form. This scientific visualization imagines what it might look like if we could peel back the outer layers to see the planetary disk and newborn star inside. Farther away from the bright stars, we find the evidence that confirms these ideas.
So when you're creating tours, essentially it's like creating a PowerPoint slide where each one of these are individual slides, and all you're doing is essentially creating starting and ending points. This is all you do. You just create a starting point and an ending point, and then the application software takes you from place to place. You can drop in text, graphics, drop in music and narration, and that's how come somebody like Benjamin can create a tour relatively easily. One of the really exciting things about Worldwide Telescope, I think, is that something like this, bringing in the rich media and the depth of resources within this program, it allows the three different kinds of learning, sort of the instructive learning where astronomers can speak directly to a kid somewhere about a particular topic or an area of research. Then the student or kid also has the ability to explore deeply within that entire resource, exploring the sky as you choose, looking anywhere in the sky. And then there's also the ability to create your own tours, sort of constructive learning. And so this particular environment, bringing all three of those opportunities together, is causing a great deal of excitement, both within the education community and others. The Hewlett Foundation is also stepping up to help us with both planning and resources for how these things, how Worldwide Telescope could be used in formal and informal learning. And so a couple weeks ago, we launched Worldwide Telescope. And the numbers that came back from the initial launch in the first 2 weeks were staggering. I mean, very, very large numbers, every single continent on Earth, including Antarctica. and I think when you think of legacy and immortality, and we think about Worldwide Telescope as one little tiny thing that Jim did that has the opportunity to inspire a whole new generation of kids, one can only imagine all the other things combined when you think about the impact of what Jim Gray has done for all of us. Thank you.
Okay, one thing that is not very well known is that there was, you heard this morning about the over-the-water search for the Tenacious. We're now going to shift in the last two talks into under the water. And it's not very well known that there was an underwater search looking for Tenacious. And Ed Saade is going to tell us about how that went.
Hi, my name's Ed Saade. I'm with a company down in San Diego called Fugro Pelagos. And we do a lot of seabed mapping, and I guess you'd have to consider us some of the end users of all the information you've been talking about today. When the previous speakers were talking about things like data exploration and science productivity, we're it. We're using exactly what you've been talking about and what you've been developing. It actually is our day-to-day activity to use these types of databases and use this technology that Jim Gray and the rest of you have been developing. It really works. It really makes a difference. So I'll give you some background on how we got involved. I'm actually sorry to say I never had the opportunity to meet Jim Gray. It's obvious from today it would have been something special, and it would have been real interesting to talk to him about what we do on the seabed relative to what we've seen so far with Terra server and the space server. There's definitely direct connection for what we can do on the seabed data. So anyway, after what happened in January of 2007, we got contacted by Donna Carnes and her team that she'd put together to try and locate the Tenacious. At the time, we were working for the state of California, mapping the seabed basically from the Golden Gate Bridge up to Point Arenas. And this is a large effort by the state to map everything from the shoreline out to the 3-mile limit in highest detail yet for all the types of purposes that you've seen with the space server and with Terra server, to do the same type of thing, to deliver data to the public and deliver data to the end users and the science community of the seabed within the 3-mile limit. So we had a 170-foot research vessel working out there, and we had an acoustic survey tool that delivers very high resolution. And when we got contacted about the ability to find the Tenacious, assuming that it had sunk and was on the seabed, we had the right tools on board, and it turned out that Donna had gone ahead and asked us to start a small survey in a couple of areas that were determined to be likely locations to begin the search. This was in early February, and we continued this activity all the way into May as the survey areas grew and grew and grew, and in the end, we wound up searching or reviewing data in an area that was equivalent to just about 300 square nautical miles, or about 1,000 square kilometers. So we started out in the areas that you see here, P1, P2, P3. These were through Donna's team, headed by a fellow that we dealt with named Bob Bilger, that the likely scenario based on the cell phone activity, based on the last known locations of the Tenacious, where would be a logical place to look on the seafloor in case the vessel had disappeared according to the sequence. And as you can see from all these boxes, this area kept growing and growing and growing as we kept finding targets and investigating targets, and without any success or any definitive location of the vessel. Then the areas up that are listed as A's, that was data that we collected for the state of California, and we also reviewed all that data, again, also looking for any evidence. So this is the big picture of what we developed in terms of the search area. The various areas were collected with acoustic sensors, and then a bunch of the red targets that you see there, we went down with underwater video equipment to actually look at targets that would be of interest, and shipwrecks that we found that turned out to be not the right ones. So the main tool that we used is what's known as a multi-beam echo sounder. As some of you know, sound travels extremely well in the water, and the advancement of technology, computer capabilities, and focusing of the transducer arrays on multi-beams has really improved remarkably over the last 10 or 15 years. And the diagram on the far left is what technology was at the end of World War II, or previous to World War II, with basically what was known as a lead line, so you could just take a spot on the seafloor and find out what the water depth was. And then as echo sounders, single beam echo sounders developed, you could get a pretty decent profile of what the seabed was like, and that really advanced the exploration of the seafloor. And now the technology with the fan of acoustic energy under the ship allows us to see in complete detail what the characteristics of the seafloor are. So we can map very accurately where the rocks are, where the rocks aren't, where the man-made features are. And the type of device that we were using, that we employed for this search, has the ability to see in terms of about 2 meter by 2 meter data density for the soundings, and on the order of about better than an order of magnitude better than that for actual imagery of the seabed. So after we would find targets of interest acoustically, we then deployed what are known as remote operated vehicles to go take a look and verify what the feature was. We did find some shipwrecks. We went down to take a look at them and verify whether they were new or old. We found things that looked like ships and turned out to be rocks, and we found a variety of other features such as fishing nets and other types of things that proved not to be the right target. So we started off with the real workhorse was the Pacific Star, which we were using for the state. And this is basically 24-hour operations where we mow the lawn, as we call it, back and forth on parallel lines, covering the seafloor anywhere from 100% to 200% coverage, just to make sure that we see every single possible target on the seafloor. We employed 3 other boats during the operation, the Michael Yule, the new Superfish out of San Francisco, and Quicksilver, which is a fishing vessel we use a lot that's out of Alaska. And we had various acoustic devices on these for mapping purposes, and we had the ROVs on 2 of them so we could expedite the search process of the optical verification. And sometimes we towed another device that's known as a side scan, which is an acoustic fan type of a device that gets a bigger area of the seafloor but doesn't provide you with the bathymetric trends that the multibeam does. So we had a whole, this is kind of a summary table of the timelines of the various vessels and the various tools that we used. We used the Pacific Star in and out of our commitments to the state of California, and of course it was February, March, April time frame, which is pretty bad weather conditions for trying to operate in the ocean environment outside of, between the Golden Gate and the Farallon Islands. So we had a lot of interruptions due to bad weather, but we stuck to it, and as the areas kept growing and expanding in the areas where we cleared and proved that the vessel wasn't there, the survey area kept expanding. This is an example of the database from the bathymetric information, the 2 meter by 2 meter data density that I spoke of. So the color coding basically varies from about, I believe, 70 meters water depth into the shallows of about 10 or 20 meters of water depth. So the database allows you to take a look at the seabed trends just as a topographic map would on the land would do it. And this gives you a good indication of where to start your search, how to expand the search, and it clears these areas. In addition, with the multi-beam system and the side scan system, we also get seabed imagery. In this case, this is a low resolution image, but you can see where the trends are of rocks. You can see the trends of geologic features on the seabed where denser material or coarser material is accumulating in those long black lines of gravels and other types of material on the seabed. This is a particularly good instrument to use for something like a man-made feature like a shipwreck, because it shows up very dark relative to a lighter background of sands and muds. This is just an example of when you mosaic all these separate lines together. You can see the lines trending northwest, southeast here, and that's how we marry it together to make an image of the seafloor to show us where the rocks are and where the features are. So this was a typical image of a likely target to be investigated. The center line down the middle is directly below the multi-beam sensor. Port and starboard is looking left and right. And this is the sensor pings along at several transmissions per second. The dark areas tend to be coarser material. The lighter areas tend to be softer material or muddier material. And then a target like that's an ideal target that stands out as a man-made feature that needs to be investigated. This is that same target when you go right over the top of it, so it has a different signature where you don't have the slant range from the center of the fish. And then the image on the right is from the video from the ROV, and you can see a rudder of a ship there. But as was the case with all the features we found, you can see it's heavily encrusted with biological organisms, which obviously means that it's been down there a long time. Anything that would have been lost new, and the time frame that we were there would have been very clean. It wouldn't have had any growth on it. This is another feature, typical feature that we investigated. All told, we had 26 or 30 targets of various types that warranted having further investigation, and again, none of them proved to be fruitful. Another image there, and the geologic conditions that you can see to the as you move up the screen for the coarser material. And you can see in the video plainly that there's fishing nets and things that hang up on some of these. But again, everything is too old and encrusted to be considered. Some more video images of rudders from another ship that we found. Then we saturated the area around the Farallon Islands, and basically the geologic conditions on the seabed around the Farallon Islands are very similar to what you see on the surface. Lots of rock outcrops, lots of very rugged area that's actually difficult to operate in. You have to be obviously careful with the surface ships as you get close to the island. So the photographic image on the right is the same type of rocks that you see that are exposed on the sea surface. And you can see that the acoustic image is very grainy and very rough looking. It's a lot harder to pick out the unique targets on that. So at times we pick out targets that do look anomalous and they turn out to be rocks, but all the features we did look in there didn't pan out. So this big data set was collected, as I said, in conjunction with the work we were doing with the state of California. It turned out that in the search for the Tenacious, we actually developed a data set very similar to the type of data set that we'd actually been sent out there originally for the state of California. So we had the opportunity to have Donna get together with the state agencies that we were involved with, and in the end, she's made a donation of the data to the state, and now the search for the Tenacious is actually complementing the entire production for the state of California, and it's a hugely worthwhile amount of information around the Farallon Islands that weren't going to get mapped any other way. So these are some of the products now that are being developed from the regular search that we do, and inclusive with the data that was for the search for the Tenacious. You can see lots of interesting outcrop features off of Half Moon Bay, and this particular one ties into the outcrop that's associated with Maverick's surf break. So the data products that now that we're going to that's been donated to the state are actually going to be used for the regular analysis that's going to be shared with the public in much the same way as the previous presentations. The volume of data that's going to be collected for the state is on the order of about, when we're all done late next year, it'll be about 200 terabytes, 250 terabytes. And needs to find a way to be better web served for all the end users and stakeholders. In addition to that, all the data collected around the Farallon Islands to the same specifications from the Tenacious search will be included in that. And then, as you can see by the logos on the bottom of these charts, there's a large group of agencies that are working together, cooperating together in a partnership on this with the USGS and Cal State University, Monterey Bay, Moss Landing, and various state agencies to develop these products and these interpretations. And this is the actual data we were collecting in concurrence with the search for the Tenacious. So these are already being web served, and the data is being available with various interpretations. You can see the resolution is pretty amazing and pretty easy to determine what's down there. And this is more of the seabed imagery of which I spoke about. So as I said, we were out there for a better part of about 3 months, 4 months, and the data set was pretty remarkable. We've worked on a lot of different searches over the years. This is as extensive a search as we've had on any other type of a topic or any other type of an effort. But I just wanted to take a moment from the state's perspective to thank Donna Carnes for actually making the data available and really pushing forward the whole database aspect. I personally now can see the tie-in between what Jim Gray was doing, and it's kind of a interesting ending that the search we did actually ties in with all that and provides some additional data quality for the state. So thank you.
And I guess it's really just a sad commentary that obviously the Tenacious is not on top of the water. And after a lot of searching, it doesn't appear to be under the water either. So it's just completely ambiguous. So our last talk before our closing is another talk on exploring the ocean by Jim Bellingham.
I'm honored to be here, and more than a little intimidated. I'm from the ocean sciences. I feel a little like a fish out of water at the moment, but I'm very proud to represent my community in this meeting. I sort of, in some sense, feel that I represent sort of what could have been. I didn't know Jim that long. I met him, I guess, in about 2004 through Ed Lazowska, who is a consummate matchmaker. And Ed, not once but several times, made sure that we had meetings because he knew that Jim Gray had an enormous amount to offer the ocean sciences. And I could tell. And actually, I have to admit, in the ocean sciences, we know that we have great data challenges. We're far behind the astronomical community. And I'd spent a fair bit of time actually looking at what the astronomers had done. So when I met Jim Gray, I knew I was talking to a special guy. So I want to talk to you about just sort of the beginning. This is a story of sort of Jim's foray into the ocean sciences. The oceans are really essential to life on Earth, and if you look at them, of course, they're beautiful and they look healthy, but beneath the waves, beneath that opaque water, things are not well, and we're increasingly learning that as we understand the impacts of human activity on the ocean, not just through global warming, but through other ways. But the challenge really is that the ocean is opaque. Right? If we stand on the shore and we look out there, we're really only looking at the surface of the ocean, and it kind of reflects, in a way, our view of the planet. Right? If we think of how we've used the ocean, we've used the ocean as a place, as a way for getting from point A to point B, point A and point B both being on land. We've used it as a place where we've extracted resources, and we've maybe in the last 70 or 80 years really intensively, increasingly tried to understand it. But the amount of information we actually have on the ocean is actually remarkably small. And so Jim's ability to take data sets, take complex data sets and give you a new method for exploring, for discovery, and for access, which in turn leads to appreciation, is something which is incredibly valuable to us in the ocean sciences. So the way I want to go through this is to give you a little bit of a feeling for how he was beginning to tie into our community. I have to give you a little bit of background on ocean sciences, and so I hope you'll indulge me here as I'll take you back a little bit through some of the things, some of the evolutions that have gone on, because ocean sciences are very much in a period of change. We're in a period of revolution. This ship here is, in fact, one of the new Coast Guard the new Coast Guard icebreaker, the Healy. You can see her here in the Arctic. And this kind of reflects sort of the pinnacle, in a way, of 20th century seagoing oceanographic science. The way we learn about the ocean is we go to sea on ships. And I saw a lot of people raise their hands in the audience when asked whether or not they'd gone sailing with Jim. I'll bet a significant fraction of you might have also experienced some seasickness. And in fact, when we go to sea on ships, we have to deal with that. We're doing our science at sea, not always under great conditions. And as a consequence, we're actually technically very conservative, which is kind of ironic if you think about it. On the one hand, we're fundamentally dependent on technology for access to what is a hostile and remote environment, but on the other hand, we don't want to try anything too new. We're a very incremental community because it costs so much to get up to this place in the Arctic. It took us so long to get there. This group probably worked, well, I know they worked for 3 years before getting there. And we get another 4 years before managing to return. And coming back with 20% of the data is better than no data. So it's a fairly conservative environment. So this is, however, not adequate for really understanding the oceans as part of the global climate system, right? And, you know, in a way, the data sets that come out of this wouldn't have been particularly interesting to Jim Gray. It's a couple of, we call it drilling holes in the ocean. What we do is we go around with a ship and we lower a wire in, make a bunch of measurements, move to the next spot. It actually gets remarkably tedious. This is sort of the new kind of oceanography that's being created. Increasingly, we're using robots and fleets of robots in the ocean, and I use the word robot very loosely. What I mean is something without a person in it that's capable of taking care of itself, taking measurements, and reporting those back to shore. And we use really a wide range of them. Some of those little systems that look like they have wings in the foreground, those are gliders, and they only weigh about 50 kilograms, so they can actually last out in the ocean for several, I think the longest deployments now are about 7 months, and they can operate in places which are really remote. And they start generating really large amounts of data, or significant amounts of data, but it's all telemetered back by satellite. There's other systems there with propellers on it, also in the foreground. Those don't last as long, but they can be used for things like mapping the seafloor. So if, for example, Jim's boat had conceivably gone down in deeper water, in 2,000 or 3,000 meter water, now some of the systems that would be used to look for it would be robots like that carrying those sonar systems rather than towing things behind a ship, which has to do with acoustics in the ocean. The other thing which is used is our satellites, of course. Now, in contrast, and we heard the story of how during the search, the views of the bay and the resolution that were needed to see a sailboat occur really very infrequently, right? The total picture of the terrestrial part of the planet is built up over years, not a matter of days. Well, in the oceans change on a period of days. So as a consequence, we actually have a set of satellite systems which, when the clouds aren't in the way, are pretty good at imaging things like the sea surface temperature, sea surface height, which tells us a lot about currents, for example. And we can actually get that information back. It's a fairly coarse resolution. It's like a kilometer resolution, but it's an integral piece of the picture. The story here is that there's no one silver bullet. There's no one tool we can use that gives us sort of a comprehensive view of the ocean. What we have are a lot of little bits and pieces, increasingly assets which actually make measurements in the ocean interior, because the ocean is deep. It's 6 kilometers, 6 kilometers in most places. And we have a set of satellites that give us a synoptic view of the surface. So one of the other interesting things I just want to mention about this is sort of the interconnected nature of the ocean. And I'll just kind of take you through sort of an example data set here. So this is the kind of data that, for example, we would take with our vehicle. We, in fact, took this data in the Arctic. You can see sort of the along track distance there along the bottom axis. It's 18 kilometers of data. Not really very long by today's standards, but this was taken under ice in the Arctic, or at least it started under ice on the left-hand side. And these are different plots of things. Temperature up there at the top, in centigrade, you can see it's kind of chilly water, and then salinity, there's an optical backscatter, oxygen, nitrate. And without going into the details here, what this tells the story of is as you come out from under the ice and you end up in a region where there's actually a little piece of the Gulf Stream, really, which has made its way into the Arctic Ocean, what you're seeing is that warm water from the Gulf Stream being mixed up to the surface. And I can tell you that complementing these measurements were a set of surface measurements, and it was really windy up there. It was really windy, and it was really cold, and the ice should have been melting. And in fact, it was dark. It was after sun had gone down for a long winter, and nonetheless, the ice was melting. So these are the types of, this kind of gives you a feeling in a way for the challenges that my colleagues who are oceanographers, who are ocean scientists, I'm more of an ocean technologist, are up against. They're dealing with a lot of little bits and pieces of information from different assets, and they're trying to piece those together to understand the global picture. And here, what's going on in the Arctic, this melting of the ice sheet, of course, has global consequences, because as you diminish that ice sheet, the sun no longer, sun, at least when it's sunny up there, no longer reflects into space, but in fact is absorbed by an ocean, which is remarkably black, contributing to basically a positive feedback cycle. So this is a piece of what we have to put together. The other point I want to make here is the large parameter space. I went through sort of a listing at one point of the parameters measured by all of the assets that we needed to make sense of, and it was about 200 or so different parameters that we're dealing with here. So I've just plotted the top culprits in this particular program. So these are all part of the dialogue that we're having with Jim, because when Jim came into us, he was thinking very much in terms of plotting things geographically, and when we said, well, no, that doesn't really quite work for us, because our things are changing much more rapidly. We have many more parameters that we need to measure. Our sample sets are fairly sparse, and what we're really about is beginning to connect things across each other. It started a dialogue, and it was an ongoing dialogue. He would come down and visit us. I would go up. He would give me a series of usually sort of a little. I mean, it was kind of a little morning session of sitting down with him by that whiteboard, and he would sort of take me through some new aspect of e-science and data systems. And largely, actually, interestingly, if I look back and I think about the lessons that I learned from him that were most valuable, it was how to understand what scientists need, how to really apply technology to the most important problems. And I was really stuck. I now realize, in a way, by this graphic. This graphic was created by a fellow, John Ryan, in our organization, and it shows sort of a 7-kilometer by 3-kilometer patch of the ocean. That gray isopycnal is basically, think of that as a constant density surface, and over that, the kind of green hatching shows where the phytoplankton are. And this shows sort of an interaction between the physical and biological ocean. We knew this happened. We never had a picture like this before. And when we started being able to measure the ocean in greater detail, these sort of pictures started evolving. And what started happening was our dialogue as technologists with the scientists started revolving around pictures. We started trying to extract from them how we could take these new data, these new tools, these better data sets they were creating, and provide them something of greater value. And the conversation always revolved around what kinds of plots that we could produce. And you can kind of see where this goes, right? I mean, the problem here, in terms of specifying requirements, right, the scientist wants to generate a zillion types of plots. They'll generate this plot, and then when they're done with this, now they don't want phytoplankton anymore, they want optical backscatter. Now they want to change this and plot it some other way. And the problem is this doesn't converge. And probably the earliest lesson I learned from Jim, he imparted to me in about 25 seconds, and it was that message that Alex has already given, which it's not about the pictures, it's about the queries. It's a 20 questions paper. And once I realized that, I realized, oh, yes. And you kind of go through and you work through that exercise, and in fact, the queries do converge. They converge on a fairly small subset from, and by the way, it's a language scientists understand very well, because they understand using search engines, even if they don't understand interacting with something like a database. And so they understand the concept of parsing together a fairly simple set of requests which can extract their information out for them. And for for me, this was really pretty, sounds very simple, I'm sure, to you all, but it was really quite transformational for us. And it led to a series of real breakthroughs. this is a picture, really, that Jim sent me. And, you know, it's not the highest quality picture because this is the one he sent me in the email. But for us, again, it was transformational, and maybe sort of illustrates a point that Jim had a mischievous side to him, because this was sort of the concluding email of a string where he kind of poked me on what, you know, well, why would you want that plot? What's the next plot you would want? What would you do with this? You know, why would you want that? And I kept sending him things back, and then he sent this collage, and a lot of these are pictures which I had sent him, and then he added on the side a set of tools, and down below a set of indexes into data sets, and this came with a whole text description of how this would be used by the scientist as a playground. And so this was kind of, this for us, we looked at this and we go, oh, yeah. And, you know, this is kind of now matched with the idea that, oh, we're providing access to the data, we're allowing them to explore the data, we're not necessarily producing their final published graphical result, although that would be nice. And then, of course, you know, the next email from Jim was something along the lines, and now he was going away for vacation for 3 months, which left us kind of hanging like, boy, this is a great idea. And he said, yeah, you know, you guys can get going on this. And in fact, we did. We did take this. And in fact, this was the tool that came out of it. And I won't take you through this in too much detail. But starting with Jim's picture there, you know, of course, we up here in the corner have that little geographical, I'll use my mouse here, we have this little geographical picture, and what is actually selected in here is a particular asset. And what we had realized in talking to Jim, and again, this was sort of part of what comes out in that conversation with him, was that we needed a very structured way of describing the data. Well, we knew that. We knew that we needed to use one of several ontologies, and like, you know, most beginners in this, we thought we would create a master ontology that would describe all oceanographic science data. We then realized that, in fact, no, a much better thing to do was to index our data against a variety of different ontologies. And so one of the things that you're able to do here is then in this pivot off of different aspects of the data. So the first column there is actually a measured parameter, and those measured parameters are hierarchical in nature. So you can see there's, you know, ocean chemistry, and under that is chlorophyll. You can expand down. Over here you have the asset that's making the measurement. And so here checked is glider. So those are those little winged vehicles that I was telling you about. They're checked, and what's happened over here is a set of things are highlighted, and they've said, and that in effect is telling you already what the observations are that are available for those particular assets in this particular region. And these columns here, it's what time the data is available and what depth the data actually covers. And so this, in just a matter of milliseconds, gives a scientist the ability to answer questions which our previous data sets, our previous data server, something called Live Access Server, which, by the way, is very widely implemented in the ocean sciences. It would literally probably take you days or weeks to do this. And as we dug into this, we realized that this was a fairly generic tool, that as long as our ontologies had this kind of hierarchical structure to them, that then, in fact, we could allow it to pivot on different aspects of it. So it's become a very general tool for us for data exploration. And so we saw this now as a way of making that data selection, finding the place where we actually have enough of those disparate pieces of information to make sense of the larger picture. So this was kind of the next step in that. And so again, you know, I would have to come back to the fact that Jim spent a lot of time talking to us, or talking to me in particular, about interacting with scientists. And I have to say, he wasn't always complimentary of scientists. He had his, you know, and I remember actually introducing him to a lot of different oceanographers, and there were some oceanographers that he very clearly said, look, I'm not going to be able to work with that person. They're just, you know, they're for a variety of reasons. And then there were other ones who he very much wanted to start up dialogues with. But one of the things that we realized was that, in fact, the scientists were very interested in having tools that let them collaborate across countries. So we we run typically by running large field programs. Those large field programs usually entail everyone coming together for a period, usually a month, maybe a couple of months at a time. And what we started developing was once we started to understand how to put the data system together in a way where the scientists could actually interact with the data quickly and efficiently, was what they really wanted was they wanted a collaborative environment that sat on top of that data system. And so this is something which we called our Collaborative Ocean Observatory Portal, and it was really largely requested by the scientists once they believed that the data system would work. And just to kind of give a picture about how Jim really has impacted my life and my lab, I've run large field programs for a long time. I started an effort back in 95, and there was a period there where I spent about 3 months a year at sea. So I have a lot of experience running field programs. 2003, we ran a particularly successful field program, but it was obvious to me in 2003 that data was our Achilles heel. We had a very difficult time working with the information in a timely fashion. So I was really primed to work with Jim. And when I talked with ONR, that was our sponsor at the time, about what we should do next, I told him that what I wanted to do is I wanted to do the data system, which worried my lab greatly because I knew that the scientists in this particular effort really weren't enthusiastic about having a large data structure. They thought README files and sending the data from place to place was just fine, thank you very much. You can go ahead and do this data system, but just don't get in our way. And after we actually put a couple of these mock-ups together, like the one which I showed you, they got so excited they said, hey, if they work that well, do we even have to come to Monterey? Because after all, we know in August it's foggy there. So, and they're right, it is indeed foggy. And in fact, we put this together, and the upshot of this has been that for an office which for 13 years, or well, no, actually 20 years now, I've developed robotic vehicles. All of the requests I get from them now are for new data system activities. And so I did this purely, I got into this as purely a defensive measure. I've got to make sure the data that's produced by my observation assets is usable by scientists. And what I found is that, in fact, the value in the data systems has greatly multiplied the utility of that data set by making it available to so many more scientists. At one time, just the scientists who used this data, that took this data would use it. Now that's multiplied by 3 or 4. So I just want to finish with this thought here that the ocean is opaque. It's opaque to our natural senses. And really, you know, when you look into so many places, when you look into space, you can see into space. You can see the moon. You can see the beauty with your natural senses. In the ocean, really, the only hope we have of really seeing the beauty and understanding the full complexity of the ocean is by being able to take all of this scientific information we have and making it accessible to the general public. And I think probably that last paper that Alex talked about is the paper which has been the most influential for me, that I thought about the most, because we realize in our community the public does not appreciate the ocean, and it's largely because you can't understand it and you can't see in it. So I have great hope that the work that Jim started in e-science will be continued into the ocean sciences, that the people that he nurtured and trained will hopefully work with us in the ocean sciences, and we'll be able to crack this nut and make this 70% of our planet, in fact, visible in cyberspace, if not through our real eyes. Thank you.
It was after we went to see Jim Bellingham at the Monterey Bay Research Institute, Monterey Bay Aquarium Research Institute, that on the way back, Donna said she thought it was time to start planning a tribute. Jim really inspired us with his beautiful descriptions of how Jim Gray had affected the work and that the work continued. And that's what Donna wanted to do. So she was driving, and I had a piece of paper, and I wrote down, I think it was the other side of the Google directions to get to the Imbarry. Anyway, and she said, okay, I want these people to talk. And she named a list. There was the list. And that is the people that you have seen. We wanted to thank you. And I'm reading the letter because Donna doesn't want to. And that's the whole support team. Every time as we went through this, Donna's very collaborative. And so as we went through the planning, on the email list or on the phone, we had Mike Olson, Gordon Bell, Ed Lazowska, Dave DeWitt, Mike Stonebreaker, Joe Hellerstein, Pat Helland, Joel Bartlett, Wendy Bartlett, all giving us good advice. Vicki Rosinski, Alan Teague, Keith Harmon worked incredibly to make this a success. As soon as we got back, and Donna said, well, where shall we have it? And I said, well, at Cal, of course. At Cal, of course. And so when we got back, I sent an email to the Dean of Engineering, Shankar Sastry. You know, everyone said, oh, he's not going to answer very quickly because he's so busy. I got an answer in an hour. Yes, of course. And so we had incredible support from the College of Engineering. Jasna Murkic, she's the person who has been organizing all of this. Just an amazing person. She's in EECS. And Miyoko, that was the one who did the programs. Aren't they gorgeous? Rachel Schaefer and April Barrett. Edward Lee is the EECS chair. Stuart Russell, of course, you've met him, is the associate chair. Without their help and support, we couldn't have done this. USNICS has provided both monetary support and also extensive in-person support from Ellie Young, Devon Shaw, and you saw the huge group of USNICS people who've been here helping us. They know how to organize big events. We didn't. This was great. ACM provided generous monetary support as well as extensive publicity. You know, it's hard. Y'all are not all in my address book or Donna's. And so it's hard to get to the right people. And so ACM really helped with the publicity, and also Pat Ryan and Monique Chang put enormous amount of their own time into this. Lots of late nights. Google provided the lunch, which was really great. Our idea was that everyone would just have to go off and find lunch. There's places to eat around here, but it was so much nicer to have it here, and it was very nice of Google to do that. Sun Microsystems also provided generous monetary support, and they did it within about 2 hours of my asking for it. I thought it was just really wonderful. IEEE also heavily publicized this. There is an angel among us. His name is Alexandros Labrinidis. I hope I'm not mispronouncing that, Alex. Alex worked so hard on the proceedings, and Sigmod underwrote the cost of the proceedings, and they're gorgeous, just gorgeous. And finally, I want to say every single person we asked to do anything gladly did that. And they gladly did that because we all love Jim so.
Of course, there's one person Paula didn't mention, and that would be Paula. A force of nature. Thank you. Thank you. It feels good to be here and to smile at Jim stories. And 16 months ago, we were not smiling. We were at the start of a very profound and intense 3-week above water search. The search was profound. The hope was profound. And the coming together of people it just blew me out of the water, literally. It was just amazing. I think I'd expected the family and the Coast Guard and a few friends and this community that came together and searched for Jim. It was truly amazing. We also lost hope at the end of the above water search. We searched underwater, and we did not find anything underwater about Tenacious. So we ended up with a profound coming together of people and the ambiguity of being lost in an enormous ocean. And now here we are, 16 months later, coming together to sing Jim's song. And I think you sing beautifully. I really do. And I just want to thank everybody for everything you've done to honor Jim. I thank you from the whole family. Jim lived life, as you well know, very forcefully, and he burnt his candle very brightly. And he would want everybody to go out and live well, and we're already doing that in our family, even as we carry the ambiguity. We, as of yesterday, have a new baby grandson. And Heather and her family are hopefully watching this via live stream, and perhaps the elder child, baby Sam, is also watching. But thank you very much for everything you've done. Thank you.
So just keep Jim's ideals as you go forward into the world from this point on. And thank you very much for coming.